When working with digital images, we need a mathematical way to read raw, messy data and extract clean, organized features. This is achieved through a specific operation called convolution, which forms the mechanical basis of many linear digital filters. To execute this operation, we need three mandatory pieces. First, the input matrix, second, a convolution kernel, and finally, the output matrix. Knowing exactly how these three components interact gives us the ability to manipulate and analyze any digital image mathematically. Step 1. We place our convolution kernel on the exact top left corner of the input matrix. We multiply corresponding elements of the overlapping regions, like a 7 and a 1, moving sequentially through the grid. Once we have the multiplication results for every overlapping cell, we add them together. We take this single final sum and place it directly into the first cell of the output matrix. Notice our output matrix is smaller than the input matrix. This is because we only calculate values where the kernel fits completely inside. Overhanging boundary edges are discarded. To get the next value, we move the kernel one step right. We repeat this sliding and summing process until we calculate every possible position. This loop is the literal definition of the convolution operation. In practice, digital inputs like RGB images have depth. They are three-dimensional matrices, which are also called tensors. To process this data, we follow a strict rule. The convolution kernel must have the exact same depth. Instead of moving a flat square, we slide an entire three-dimensional volume cube through the input. We multiply elements across the volume and sum them up. The resulting output loses its depth entirely, becoming a flat, single-layer matrix. Adding depth allows the filter to handle multi-layered color channels, while the core math compresses that data into a single unified feature map. To see how this math yields a tangible result, a grayscale photograph sits on the left, beside our calculated output canvas on the right. The red box is our filter, and the green box is the image patch being calculated. Because of the values inside this kernel, the filter detects vertical edges, dynamically rendering them onto the output canvas as it scans. By swapping the numbers inside the kernel, we instantly change the filter's behavior. We can calculate a blurred output, or switch the values again to sharpen the image. Extracting different low-level features from an image relies entirely on the specific numbers you feed into your kernel. We have broken down how convolution mathematically multiplies and adds overlapping regions to create a new output matrix. We established that for three-dimensional tensors, neural network filters must have the exact same number of channels as the input. And we mapped how strict mathematical rules are used practically for extracting low-level features from photographs. Take a moment to test this yourself. Look at the values in this single patch and calculate the convolution output manually. By walking through the arithmetic step by step, a complex algorithmic process simply becomes a mechanical, transparent tool you can control.